This is the fourth part in the series, An Introduction to the Derivative, and in this case we're going to look at a second situation where a function is non-differentiable. Here we're looking at the function f of x equals the absolute value of x minus 2, and we're going to use the alternate form of the derivative again, and we're going to be looking at this as x approaches 2. So let's go ahead and write down the alternate form of the derivative. So we have the limit as x approaches c of f of x minus f of c all over x minus c. In this case our c is 2, so we have the limit as x approaches 2 of f of x is x minus 2, absolute value, minus f of 2 over x minus c, which is 2. And this gives us the limit as x approaches 2 of x minus 2 minus f of 2. If we put a 2 in here, we have 2 minus 2, which is 0. Minus 0 of x minus 2, which is equal to the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. Now what we're going to do with this limit is we're going to take this limit from the left and from the right. So first, let's look at the limit from the left. As x approaches 2 from the left of x minus 2 over x minus 2. Now, if we evaluate this, at a value of x to the left of 2, x is less than 2. So x less than 2 is a number smaller than 2, minus 2 is a negative number. A negative number with the absolute value is a positive number. A number less than 2 minus 2 is negative, so we have a positive divided by a negative. Now this is the same number in the numerator and denominator, so it's going to be a negative 1. Now let's take a look at that same limit from the right. Now we have x minus 2, absolute value, over x minus 2. In this case now, x is to the right of 2, which is greater than 2. So a number greater than 2 minus 2 is positive. A number greater than 2 minus 2 is positive. They're again the same number in the numerator and denominator. Positive divided by positive is a positive number, which is positive 1. Now, an important thing to note here is this function is not graphed here. What you see in the graph here is the graph of our original function, absolute value of x minus 2. This is a common mistake that people make in trying to evaluate these limits and thinking that this is the function that they're evaluating, and they kind of get twisted in knots. So again, this is the graph of this function, not this. And notice what we see here. This limit gives us the slope of the tangent line of this original function. Notice the slope of this line here is negative 1, and the slope on this side of 2 is positive 1. So an interesting artifact there. But as we can see, the limit from the left does not equal the limit from the right. And if you recall our discussion on the existence of limits, if the limit of a function is different from the left and the right, that limit does not exist. And so, by the limit definition of derivative, this function f of x is non-differentiable at x equals 2. And in general, any function that has a sharp turn is going to be non-differentiable at that turning point. Let's move on now to the third condition in which a function is non-differentiable. In this situation, we have the graph of the function f of x equals x to the 1/3. And as usual, we're going to evaluate this function using the alternative form of the derivative, which is limit as x approaches c of f of x minus f of c over x minus c. In this case, we're going to evaluate this limit at x equals 0. So the limit as x approaches 0 of f of x, which is x to the 1/3, minus f of c, which is 0, all over x minus c, which is 0. This gives us x to the 1/3 minus f of 0 is 0. X minus 0 is x. So, if we simplify this, 1/3 minus 3/3 is x to the negative 2/3, which is 1 over x to the 2/3. Now let's take that limit. Of 1 over x to the 2/3. Now if we evaluate this limit, there's really no simplification that we can do here. And the only alternative is to let x go to 0. And as x goes to 0, either from the left or from the right, it doesn't really matter. This function is approaching infinity. And so this limit does not exist because it goes to infinity. So you can see that the derivative of this function at x equals 0 is undefined. And so this function is non-differentiable at x equals 0. And the reason is because the slope of our tangent line, which is what this gives us, at x equals 0 is infinity, which is undefined. So we have an undefined slope, which is a vertical tangent line. So where we have vertical tangent lines, we're non-differentiable. Now these three conditions lead us to a very interesting conclusion. And if we bring back those functions, we'll recall that if a function is discontinuous, it's non-differentiable at the discontinuity. But even if a function is continuous, that doesn't always guarantee differentiability. This function is continuous, yet it's non-differentiable here, and this function is continuous, yet it's non-differentiable here. So continuity does not imply differentiability. On the other hand, differentiability does imply continuity, and that's something you should take note of because it will be very useful later on. Now, up to this point, our discussion of derivatives have been centered around the limit definition of derivative and the alternative form, which is also a limit definition. And as you can probably tell very quickly with any complex function, the limit definition is going to become very cumbersome. But fear not, we have several rules that we're going to look at that are going to significantly improve our situation and help us mechanically with the differentiation of various functions. So let's go ahead and start reviewing the rules of differentiation. Now the first rule that we're going to look at is the constant rule. And the constant rule says the derivative with respect to x of some constant value is equal to 0. Now this is fairly easy to see if you just imagine what this is talking about. Really roughly, we have an xy coordinate grid, and let's say that y equals 2. So we have some dotted function, and this is the function y equals 2. You can see that since the derivative is the slope of the tangent line and the slope of a horizontal line is 0, clearly the derivative of any constant is going to be the slope of a horizontal line, which is just 0. So that's a pretty basic idea there. So that's the constant rule, and we'll be employing that fairly regularly. Now the next rule we're going to look at is the power rule, and this is arguably one of the most important rules in differentiation. And the power rule says the derivative with respect to x of some variable function to the nth degree is equal to the degree times the function to the degree minus 1. So as an example, let's take a very simple function. The derivative with respect to x of x squared. So what we do is we take the degree, pull it down in front, and we subtract 1 from the degree. So it's x to the 1. We don't write the x to the 1. So the derivative of x squared is 2x. Let's try something a little different. Derivative with respect to x of the square root of x. Now, it might be easier to rewrite this as a rational exponent. So this is the derivative with respect to x of x to the 1/2. And that's going to be, we pull down the exponent, so 1/2 x, and we subtract 1 from the exponent. Well, 1/2 minus 2/2 is -1/2. And to simplify that, it becomes 1 over 2x to the 1/2. And if you want to put it back into radical form, it's 1 over 2 square roots of x. But it's not necessary to put it in that form. So let's try one more. And this one is going to be derivative with respect to x of 1 over x squared. In this case, when we rewrite it, we're going to do the derivative with respect to x of x to the -2. And to take the derivative of that, we're just going to have pull down the exponent, -2, x, subtract 1, -3. And that'll be equal to -2 over x to the 3rd. And that's the power rule. If you're interested in the proofs of any of these rules, please feel free to check out the other videos that I've produced, and I've generated proofs for almost all these rules.